Hello students. Now the last topic related to the capacitor is energy stored in capacitor. We know that capacitor is a device which is used to store electrical charge and the electrical energy, and it is widely used in all electrical and electronic device. Now the question is, how much energy, or what is an expression for energy stored in capacitor, and how a capacitor store energy. Now we know that the capacitor is a system of two conductors separated by a dielectric or insulating medium, and the amount of charge deposited on one plate is plus Q and on other plate it is minus Q. The total charge on the capacitor, if we say the total charge of a system, it is 0, but we say Q is the amount of charge the capacitor stores. Now let us consider that initially the two conductors are uncharged. So this is our final situation. We need to deposit plus Q charge on one plate and minus Q charge on the another plate. Initially, we assume that both the conductors, say this is conductor 1, this is conductor 2, are uncharged. Now, work is required to be done to deposit charge on the plates of the capacitor, and this work is done by a battery. Now when we have to find out the energy stored in a capacitor, we consider some intermediate position. Initial, now what is it? Is an uncharged capacitor, so initial charge is 0. The final charge which we have to obtain is plus Q charge on the plate of a capacitor. So this is the initial condition, this is the final condition. So initial energy is 0, final energy we have to derive. So in such a situation, we consider an intermediate situation where we assume some charge is already deposited on the plates of capacitor. For example, initially both the plates are uncharged, or initially the capacitor is uncharged. So no charge is deposited on the plate. So we say it is 0 coulomb. And suppose I need to deposit 5 coulomb of charge on the plates of capacitor. So work is required to be done against the electric field, and so we connect a battery. Now we consider an intermediate position, and the work should be done bit by bit, or in such a way that acceleration is 0 or the velocity remains constant when a charge is moved from one point to the another. So let us consider some intermediate position where the charge on this is Q dash minus Q dash and the charge on this is plus Q dash. And the electric field established, the final electric field, if you remember, is established, and that E was equal to sigma upon epsilon naught. Now this is an intermediate position. So initial 0, final we need to deposit 5 coulomb of charge. Let us assume this is an intermediate position where 1 coulomb of charge is deposited. So the electric field established is less than the 5 coulomb. This is the final situation, this was the initial situation. 1 coulomb is an intermediate position. So the first step is we find out the potential at this instant. So let the potential is V dash, that is equal to Q dash upon C. So this is the equation number 1. So this is an intermediate position, in between position. Now the work has to be done to move a unit positive charge from one plate to the another. So we assume that the small amount of charge delta Q dash plus, that is a unit positive charge, is moved from plate 2 to plate 1 or conductor 2 to conductor 1. So what will happen in this situation? The charge on this plate becomes minus Q dash minus delta Q dash. The positive charge has been removed from it. We assume that actually how the capacitor gets charged, with the help of a battery, the electrons are removed from this. So this plate becomes positively charged and the induced charges are on the surface of the second plate. This is the theory. This is the concept. When we connect a battery positive and negative terminal, the electrons are being removed from this plate, that is the free electron. This plate becomes positively charged. As a result, induction takes place on second charge. But the other way to look the same process is, if I want to make any body negatively charged, I have to remove the positive charge from it. So I remove 1 plus delta Q dash charge from this plate. So this plate will become more negative, or this plate becomes Q dash plus delta Q dash. So say initially it was 0, finally you have to go to the 5 coulomb. This is already 1 coulomb is already deposited, so potential at this time is this. Now the charge is deposited or work is done bit by bit. So delta Q dash charge, a unit positive charge is moved. Now say the charge deposited is 1.1 coulomb. It means the intermediate position the charge was 1 coulomb and now it is 1.1. So small amount of work done to deposit additional delta Q dash charges, delta W is equal to potential. First we find out the potential to find the energy and then we multiply it by a test charge. So V dash delta Q dash. This much amount of work is done to deposit additional delta Q dash charge. Therefore, delta W is equal to Q dash by C delta Q dash. Now we want to deposit total amount of charge which has to be deposited is Q or 5 coulomb. So integrating this equation, total work done, W is equal to integration of delta W, and the limit becomes initial, that is uncharged, to the final capital Q, and this is equal to integration limit 0 to Q, Q dash by C delta Q dash. So we have to integrate this with respect to Q dash, and therefore the work done is equal to 1 by C. Now integration Q dash delta Q dash, that is Q dash square by 2, and the limit becomes 0 to Q. Therefore work done is equal to Q dash square, that is final minus initial, so Q square by 2C. This much work has to be done to deposit or to make a capacitor store up energy. So this much energy is stored, and this work done is denoted by U, capital U, or we can also say it is the energy or potential energy stored in the capacitor. So one formula for the potential energy stored in the capacitor is half Q square by C. Now see the different forms of equation. We know that in the end, when the capacitor is fully charged, Q can be written as CV, and therefore let us name this as equation 1. So substitute Q is equal to CV in this equation. We will find U is equal to half C square V square, 1 C is cancelled. So another formula is half CV square. So one formula in the terms of Q and C, other formula in the terms of C and V. Now one formula left is in the form of Q and V. So from this equation also I can write C is equal to Q by V, and then I substitute this in equation 1. So U is equal to half. In the place of C I write Q by V, V goes up, Q cancelled, so half QV. So we have three different forms or three expression for the energy stored in capacitor. Depending upon the values given to us, we can use any of this expression in the numerical. So this is how the capacitor store energy. Initially it is uncharged, then work is done by a battery. We assume that the unit positive charge is moved from conductor 2 to conductor 1. We took some intermediate position because initially it was 0, finally you have to go up to Q. An intermediate position, and then the additional charge was or additional work was done, that is delta Q dash. So additional work done is equal to the potential multiplied by the additional charge which you have deposited, and then we integrate the equation, and by substitution method we have three different forms of equation. Now another topic related is energy density of electric field. We know a capacitor store electrical energy in the form of an electric field. So if we consider a capacitor having area A, distance D and capacitance C, then we can find out the energy density. Now energy density means energy per unit volume. So energy density of electric field, because we have energy density of magnetic field also and energy density of electromagnetic waves also. So we denote this as rho E, E for electric field, and it is defined as energy per unit volume. So energy density is defined as energy stored per unit volume. Here we take an example of capacitor. Now energy stored in the capacitor, so expression for the energy we have derived, that is half CV square, half Q square by C or half QV. There are three different expression for you. You can use any of that expression. Now the widely used expression is half CV square. This is the widely used expression. The other expression was half Q square by C, and the third expression was half Q into V. So we take the help of this energy stored in a capacitor. So energy stored in capacitor is half CV square. Also we can write SI unit of energy density is joule per meter cube, and dimensional formula you write it by yourself, it is left as an exercise. So SI unit of energy density is joule per meter cube. How much energy is stored in the volume 1 meter cube. Now energy formula is half C V square, capital V. Now if I take an example of a capacitor, volume can be written as area into the length or the distance between the two plates. So rho E is equal to half. Now in the place of C I write epsilon naught A by D, that is C is equal to epsilon naught A by D. This is V, V is a potential, so V square upon the volume, that is A into D. So area gets cancelled. So rho E is equal to half epsilon naught V square upon D square. Now we know that electric field intensity is equal to V square upon, E square can be written as V square by D square, because E is equal to V by D, and therefore rho E can be written as half epsilon naught E square. So this is an expression for energy density of electric field or energy density of a capacitor. Say if you use this formula half Q square by C, in the place of Q you can write sigma into A, and then C can be written as epsilon naught A by D. Then if we want E is also equal to sigma upon epsilon. So you can again come to this relation. So by taking the help of any of these three equations, I can come to the same conclusion. So this is the energy density of electric field or energy density of a capacitor. Now again the subtopic, energy stored in combination of capacitor. We have seen that the capacitor can be connected in two ways, the series combination and the parallel combination. So suppose the capacitors are connected in series. So when we consider a series combination of capacitor, we know that the charge deposited on each capacitor is same, but potential difference is different. So if n capacitors are connected in series and the energy stored in each capacitor is U1, U2 dash 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 Un. So you have C1, C2, C3 dash 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 Cn connected in series, and the energy stored is U1, U2 dash 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 Un respectively. So if I want to find out the total energy stored in the series combination, so U is equal to U1 plus U2 plus U3 plus dash dash dash, that is Un. Now since the charge on each capacitor remains same, I will be using the formula half Q square by C. So Q square is taken as common, so half C1, half Q square 1 upon C1 plus 1 upon C2 plus dash 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 1 upon Cn. So this is the total energy stored in the series combination of a capacitor. It will be easier to use this formula because Q is constant. Similarly, if we have a parallel combination, suppose we have a parallel combination. So now in parallel combination, again C1 to Cn is connected in parallel, U1 and U2 are the respective energy stored. Now in parallel combination, the charge is different but potential difference is same. So I will write U is equal to U1 plus U2 plus dash 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 plus Un, and now it becomes half CV square. So V square is taken as common, so C1 plus C2 plus dash 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 Cn. So whether your combination is series or a parallel, you have to do U is equal to U1 plus U2 plus dash 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 Un, and you have to consider whether the charge is same or a potential difference is same. You have to find out the quantity which is same. It will be easier as we can take it out the common from that all the quantities. So you have to remember that whether it is a series combination or a parallel combination, the total energy is the sum of the individual energy. Now individual energy, so whether you use this formula or you can find out Q1, Q2, Q3, then you can use this formula here, but here Q1, Q2, Q3 will comes into picture, so it will be individual term you have to calculate. So instead of this, if there is a parallel combination and V is given, we can take V square as a common and it becomes C1 plus C2 plus Cn. So this is about the energy stored in the capacitor. So here we complete the second part of the chapter, capacitor. Also we end our chapter 2 theory portion. Now the last topic which is given in the book is Van de Graaff generator. So there is one device which is given is Van de Graaff generator. Now this portion or this topic is not included in our Gujarat board syllabus, but we need to understand this device also, and most important we have to understand its principle. So the principle of Van de Graaff generator, and a Van de Graaff generator is a device for the let me give you the information. The detailed principle and the working of Van de Graaff generator we will discuss in the lecture of NEET and JEE. Van de Graaff generator is a device which is used to create a large potential difference. So if we need a large potential difference, then we take the help of a device which is called Van de Graaff generator. So it generates a very large potential difference about 10 raised to 6 volt or about 1 million volt. So this is a very high potential difference this device can generate, and it is the name of a scientist who constructed this generator. So whenever we need a large potential difference in any application, we will take the help of Van de Graaff generator, and it works on some principle. The principle is more important as compared to the working of Van de Graaff generator. So we end our chapter 2 theory portion in this lecture, and we will also discuss the Van de Graaff generator and its principle whenever we will be doing JEE and NEET portion. So we will be starting illustrations and the textual exercise in the coming lectures. Have a good day.